So for those of you who were not there in the previous talk, Paul Lemire from KDAB, one of the Q3D maintainers. I do some contributions occasionally. And today we're going to talk about one of the features in Q3D that probably nobody has really seen unless you've been playing with the sources. That's something we call the node editor and the shader generator. But before we actually dive into that concept, we must all agree on what a shader is. So we'll do a quick recap about that. So what are shaders? Well, essentially programs that run on GPUs. Okay? And there are different types of shaders: vertex, fragment, geometry, compute, whatever name you want. What really changes about those type of shaders is that they all compute something, but inputs or outputs might be different. Okay? Usually there are two big languages into which you would write your shaders. If you're using OpenGL, that would be GLSL, DirectX HLSL. And now with modern graphics API, there are a few more options. We'll try to cover that with a slide in a few minutes. So what do we use shaders for? Well, typically what happens is you're going to create your geometry by creating triangles. Those triangles, you're going to put them in the buffer that you're going to upload into GPU memory. Or at least you are hoping the driver will do that for you, but that's the idea. And let's say you want to view your geometry from a point of view that might be changing. You might be moving your camera around. To do that, we will create what we call a vertex shader, a shader that works on vertices, which is a fancy word for saying points in 3D space, really. And in that shader, what we're actually doing is transforming our points based on the viewpoint of the camera. Okay? Once that's done, so that's one part of the graphics pipeline. Once that's done, the rest of the graphics pipeline, we will do essentially two steps. The first one is called the primitive assembly, so creating a triangle from three transformed vertices. And once we've reached that point, we'll enter another step, which is the rasterization. The rasterization is converting a surface into a given number of fragments or pixels. Okay, so getting to that point. Once that rasterization is done, a given number of fragment shader instances are going to be called to color in parallel all the pixels that are composed by that area on screen. And fragment shader is fragment is also a fancy word for saying pixels. Okay, typically you find that in OpenGL. If you're using DirectX, they call that pixel shader, which might make sense. So what's the actual code for such shader? What could it look like? If we look at the vertex shader, essentially we will have a version directive saying that we're going to use the GLSL version 150, and 150 is for OpenGL 3.2, obvious. And we moved on, well, if you wonder what's the version number for OpenGL 3.3, it's not 160, it's 330. They decided to create something that made sense only after 3.3, unfortunately, but yeah. So we've got our version directive, we've got our input. Our input is a vector of 3 floats, which is the position of our vertex. Okay, and also we've got something called a uniform. You can view the uniform as a variable that is going to be constant for all the instances of your vertex shader. So remember, we're drawing a triangle, so we've got 3 vertices. Well, we're going to execute that code 3 times, where each time we will get a different vertex position, but the uniform matrix would be the same. And that uniform, called MVP, for model view projection essentially contains the camera transformations. So what we're going to do in our vertex shader is write into a specific variable called GL position, and GL position is going to contain the transform vertex position. Okay? So if you've got 3 vertices, we're going to have only 3 instances of that shader executed on the GPU, but if you had millions of vertices, you would probably get not millions, but thousands of instances of that shader executed in parallel at the same time on the GPU. So that scales quite well. For the fragment shader, so remember, we transform the position, primitive assembly takes place, rasterization, converting your surface into pixels, and then to color each pixel, we're calling the fragment shader. And our fragment shader, in our case, is not receiving any inputs, technically cooled, but we try to keep things simple, and we're outputting only a vec4, which is an RGBA color, okay, in linear space here. So what we're doing in our main function is frag color equals a vec4 where we're fully red, no green, no blue, and fully opaque, no transparency. Now, so that was a quick recap about shader to get you to understand what we're going to talk about. Because in practice, if you're using Qt3D, that's the way you will load your shaders. You use the material API, which allows you to reference an effect. The effect can have 1 or more techniques, okay? And each technique has a graphics API filter, which essentially says to Qt3D, well, we expect that to be run against that version of OpenGL. And if the hardware you're running on doesn't have that version, we will just ignore that technique. Okay? And in the technique, you can specify 1 or more render passes, usually 1, which will contain your shader program, which you will load from a file, typically. Or you could write it in line, but that gets a bit messier. Now, when we talk about shaders with OpenGL, there are a few issues. Well, the bad thing in a way is that there are multiple OpenGL versions on desktop and on embedded. And each version allows you to do slightly different things and uses a slightly different syntax. So that means if you create an application and you want your application to work on pretty much any OpenGL capable desktop in the world, well, you need to provide a shader for pretty much all of these versions, which is not great. The other thing really important about shaders and OpenGL is that OpenGL expects that you will provide the code of your shaders as GLSL code. Okay? And that code will be compiled by the OpenGL driver at runtime into executable code for the GPU. And that's where, it's better to have a nice OpenGL driver, because if it's not the case, you might have issues with a shader, compiling a shader that looks totally correct. It happens sometimes. Now, let's quickly talk about Vulkan, and I suspect it's the case with other modern graphics APIs that they don't expect you to provide the shader code as GLSL or actual programming code. They expect you to provide the shader code as a precompiled bytecode. In the case of Vulkan, that's called SPIRV. And that means that we're not compiling shaders at runtime anymore. That process has to take place beforehand, usually at build time, and you've got tooling around that to do so. The nice thing with that is that you're not stuck with GLSL anymore. You could use other programming language as long as you're able to convert to SPIRV after. Now, if we get back to the case of having to handle different APIs or different OpenGL versions in your applications, more specifically with Qt3D, two options. As we said, one would be to generate a shader for each OpenGL version. That's more assets to handle and deploy. That's probably harder to test as well, because well, you need to test every possible combination. And yeah, that might not be the best way of doing things. The other approach is that instead of writing shader code directly, you go with an abstraction. You abstract your shader code and you try to generate it at runtime based on what you know the hardware is capable of. And that's an approach we went for with the node editor, where we actually get to the point of what that talk really is about. And the idea, we didn't invent anything. We just, created something that others have done before to handle some cases in Qt3D. The idea is we would have nodes which can be input, outputs, or operation nodes. And we would create a graph. Okay, we'll instantiate those nodes and connect the inputs of one node to the inputs of the others to actually create a shader that would make sense. What we've done with that tool, which I'll show you in a couple minutes, is that we export what we call .graph files, which contain two things: the definitions of the nodes, as well as the structure of the graph. And the definition of a node is what we call a prototype. The node editor tool is not yet published. It will be soon. We just have a few issues to work out, and it will likely be bundled as part of our Quasar framework, and also available as a Qt Creator plugin. So let's get back to nodes. As I was saying, we've got prototypes, or node definitions, if you want. And the prototype is going to contain a few information. It's easier if we move directly to the actual code. So we use a JSON-based description. And let's say we want to create a node, an operation node called add. That node will receive two inputs, first and second, and it will have a single output, the sum. Okay? Parameters is going to allow us to specify the type of the inputs and outputs. In our case, typically, the type that we'll be adding will be the same as the second type we'll be adding, and that will determine the output type as well. So what we've decided is by default, the type will be a vector of 3 floats. And then we get to the interesting part, which is called rules, which is the actual translation for that node. So first, we specify in one of those rules the format, so essentially which API that translation is for. So we've got one for OpenGL ES2. And the substitution rule is IP $type $sum equals $first plus $second. And anything with a $sign gets actually transformed by the actual values in the inputs or outputs, or types, for that matter. And we've got the same thing for OpenGL Desktop Core Profile 3.0. And you can notice that on that one, we pretty much have the same thing, except that we don't have that IP precision qualifier. Okay? And if you add, other graphics API, you could add whatever you want the translation to be. And you can create slightly more complex prototypes by using the header snippets declaration in your rules, which allow you to include directly a bit of GLSL code. So that's useful sometimes to if you do not want to create a huge graph because you decided to do everything with add, multiply, sometimes it's just easier to wrap that into a function, into your own prototype and instantiate that. Sorry. Layers, we'll get back to that in a second. We'll actually have a look at the node editor. So yeah, that's what it looks like nothing really impressive. Sorry, I cannot really increase the size of the name. But I'll try to give you, well, to show you what they do. So let's open up a graph that we're using for our Creza project, which is our gamma correction and tone mapping shader, so that we can get an idea of how that would work. Let's forget about that part for now. And let's look at what we're doing. So we've added an input node. We're saying that we're going to receive an input called text coords, which will be a vector of 2 floats. That's typically how you get your texture coordinates in OpenGL. Next, we're using those texture coordinates to sample, to look up a pixel value into a texture. And we're specifying the name of the texture to be used right there on top. Okay? And we're doing 2 things with that color. So when you sample from a texture, you get a vector, which is a color, RGB, plus the alpha, the transparency that you might have in that color. What we're doing in our graph is separating the alpha from the color part. And to do that, we create a swizzle node. Okay? And in that swizzle node, we specify that as an input, receive a vector, that we will output a vec3, and that we will select the members R, G, and B from our initial vec4 to create the vec3. We do that, we connect, therefore, the output of our node, which is a vec3, to a specific node we've made called the exposure correction, which, given a color and another input called final exposure, applies exposure to brighten or darken a given color. Okay, so far, more or less. If you notice there, from that sample texture, we've connected the output to another node, another swizzle node, where we're extracting only the transparency part, which will be forwarded later down into the pipeline. Okay. Now, if we get back to the actual transformed color after the exposure correction, we're then feeding that into another custom node called Quasar Gamma Correction, where we're applying the gamma correction based on another input called gamma of type float. Okay, and we're combining everything. We're using the output color, which is a vec3 RGB, and combining it with the alpha color, the alpha value we got from our initial texture lookup. We're combining the two to form a vec4 again, which we're outputting as our fragment color, as our pixel color. But that's just to show you the type of things you can do with the node editor. But if we were to start a new instance of that, we could create, a small fragment shader that's going to output a color, which is the addition of 2 constant values. So what I'll do first is create 2 constant value. So that one is constant. I'll modify their type to be vec3. Vec3 is a vector of 3 floats. One will be red. The other will be green. I'll use the add node to actually add the 2 together. If I can click correctly. So I get the sum of that. I want to output the final pixel color, and to do that, you need to write into a special variable called glFragColor. We've created a frag color node for that. The only issue is I'm dealing with vec3, and frag color is expecting a vec4. Okay, so I need to transform my vector into a vec4, and I can do that with a node called join2, which will join two vectors. And you've got a few options you can set. I'm going to set that the output type will be a vec4. The first parameter will be a vec3. And to make a vec4 from a vec3, you need to add a single float. So last parameter is fine. So we can now connect the sum, which is a vec3, and use the output of that to feed our frag caller. And ideally, either I'd create a constant or put a value which specifies what the fourth member of our vec4 is to be. And since I don't want any transparency, let's go for one. That gives you an idea of how you would write a shader with that kind of tooling. Is it the right one? Yeah. So now that we've seen how you can use that node editor, well, that's nice, but how does that work with Qt3D? Well, I didn't show you, but you've got a file save menu, and that generates for you the .graph file. And if you want to use that graph file, inside Qt3D, you will essentially go to one class called the QShader Program Builder. QShader Program Builder is going to look at your graph file, at the definitions of the nodes. It's going to look at what your hardware is capable of, and it's going to actually generate the shader code, do some optimization at the same time, removing temporaries and so on, so that you get a shader you can work with. How do you use that? Well, you use pretty much the same material API we saw earlier. So you've got a material, an effect, techniques. Nothing really changes until you get to the render pass. In the render pass, you still specify your shader program, except that you're not going to load the GLSL code from the sources. You're going to use one or more shader program builders to generate the code for the fragment shader, and another shader program builder to generate the code for the vertex shader. Okay. I realize I didn't talk about the layers. So let me get back to that really quickly. Right. Sometimes you might want to handle different algorithms or different code paths within a shader graph. Okay? And to do that, we've got that notion of layer, but we're not totally satisfied with it, to be honest, but it works good enough for now. But the idea is you essentially can define part of the graph as belonging to a given layer. And when you instantiate your shader graph, you can say, I want to enable or disable that layer. So as you can see in here, we've got all layers enabled, and it's a mess, and it's not going to be producing a shader we can work with. But the idea we did, and the shader code we saw a bit earlier, was a shader code where we would essentially be doing the exposure correction and the gamma correction, but no tone mapping whatsoever, because we had the no tone map layer enabled. If I were to remove that, we can see that the connection between the exposure correction and the gamma correction has not been made. That's because that's a shader graph where we expect at least one layer to be enabled. Now, let's say I want to use the filmic tone mapping. I could enable that, and you can see that a new node and two connections, two edges are being added. If we look on the side, we can see that that node belongs to the use filmic tone map layer. And that's essentially the way we can have shaders with different types of algorithms, different type of entries. Sometimes you might want to look from a value from a texture. In other cases, you want to provide it from a constant value. So that's where layers might be useful. And to get back to that point, when you're loading your shader program with a shader program builder, you would have to specify the name of the layers you want to use when generating the shader code. Okay. So we've pretty much covered everything there is to cover with the actual state of the shader builder. What's next, and I'll finish really quickly, is we think we might be able to reuse that concept of nodes to actually do more things with Qt3D, such as creating frame graphs, creating logical devices, or maybe even later on create particle systems where you will have, let's say, an emitter node that you connect to some wind turbulence node, and at the end it creates, a very complex particle system. That's one thing. The other thing is we discussed briefly about Vulkan. Vulkan expects Pervy to be bytecode. Maybe we could have the shader builder be used as a build time tool to actually traverse the graph and generate the bytecode at that point for us as well. Those are just ideas, but those are likely things we might be doing if you've got some time to do that. And that concludes the talk. Thank you, guys.
Yes, thank you. So we might have time for one very quick question, if there's any. Yes?
Yeah, all this reminds me a lot of Blender, if you know Blender,
Yeah.
the same node editor. So it's really the same principle, basically, isn't it?
Exactly, except that we could argue that the nodes in Blender are a bit higher level. You don't have, well, you have them as well. You also have the add and so on, but usually they provide us with nodes which are a bit, well, doing a bit of magic behind the scenes, and you don't get the idea. But yeah, that's the same concept. Nothing really new in what we did.
So yesterday I learned that it was possible to export a model, a 3D model with Blender, and to import it into Qt3D. Does that mean that we can also export the shaders from Blender and import them in Qt3D directly?
Depends how you do that. If you use Quasar, which is our framework to do the export, we convert everything to GLTF2. Well, we ask Blender to convert everything to GLTF2. And if you use the principled BSDF shader, I think in Blender, you get that directly in Qt3D. However, if you've created your own custom cycles material in Blender, right now, that won't work. But that's something we're like, yeah, maybe we could do it if we replicate all the nodes in our node editor as well.
Great, thank you.
All right, thanks again, Paul.
Thank you.